All right. You ready?
Only the best show.
Yeah. All right, Trevor.
I'm sorry, what?
You ready?
Yeah, sorry.
Okay. Let's get loose. Let's get everybody to stop. Nothing gets you looser than getting a piece of notebook paper.
Pardon the interruption.
Okay. So, probably none of this looks like it makes any sense, which is fine. I'm just giving you a picture of the end of today, what we'll know. Okay? We'll at least know what these formulas mean. So first, let me give you a little bit of explanation. This P right here stands for permutations. This guy right here, we need to understand what this means, okay? What does this mean? It means n, we can read it like this, n factorial. So what does n factorial mean? That's what we're going to learn. That's something we're going to learn. And of course, then this would be n minus r factorial. And one thing that's real key that you may want to just write down here at the very beginning of this whole thing, because it's going to become like a decision-making tool. For permutations, we say something like order matters or is important. And down here, I don't really need to tell you what how to read factorial again, but I would tell you that it stands for combinations. C stands for combinations. And that basically we can interpret as order matters. The nitty-gritty, bare-bones stuff that you need to know about these two formulas. Right. So we're going to start with permutations. That would be this guy right here. But before we can do permutations, and before we can know before we can do permutations, we have to understand what factorial means. But before we can understand what factorial means, we have to talk about something called the fundamental counting principle. Okay, which is something I'm sure you're familiar with. I'm sure you have at some time been exposed to it, whether it had a name or it didn't. You have done the fundamental counting principle before. So let's start there. Okay. So I'm not starting with permutation, starting with fundamental theorem, fundamental counting principle. That will take us into permutations. Okay. We're going to use something called tree diagrams to talk about the fundamental counting principle. So before you sit a six-sided die in a quarter, can you imagine that? Yep, can you imagine a six-sided die and a quarter right next to each other? Yeah. Oh, good grief. Smart Alex. A dime, or die, a die, and then a quarter right next to it. You're going to roll the die, and then you're going to flip the quarter, okay? So what could possibly be an outcome? Well, you roll a 2, and you get heads, right? That's one possible outcome. What's another possible outcome? 2 and a tails. Another one?
5 and it lands on its side.
Not gonna happen.
It's gonna happen someday.
Nope.
5 and heads.
Very well
5 and
could
heads. Hey, I'm glad that you're adding to class and not taking away from it, because it's really helping everyone out. All right. So, how do we count all of the ways that everything could happen? Okay. So we're laying a foundation for first factorials, and then permutations, and then combinations. Anybody? I mean, we could do this, right? We could do 1 and a heads. We could have 2 and a heads. We could have 3 and a heads. And we can kind of go about it in an orderly fashion that way and count them all up. How many would you think there would be if you counted them all up? 12, okay. Now how did you get to that quickly? 6 times 2. So have you done this before? Okay. So what we call rolling a die, that's what we're going to call an event. Event A. And when you flip a quarter, we're going to call that event B. In a really dry and boring way, the fundamental counting principle applies to a series of events. A series of events is called an outcome. So the number of outcomes, meaning the number of combinations or ways that event A and then event B can happen, would be the number of ways event A can happen times the number of ways event B can happen. But here's a much better way to at least visualize it. Okay? So here you are. Before you ever do anything regarding this die and this quarter. Okay? So before you roll the die, you pick it up in your hand. How many different ways can that event end when you roll that die? 6 different ways. Okay. This one ends in a 1, this one a 2, this one a 3, this one a 4, 5, this one a 6. So each of these lines we call a branch. And you can go down any of these branches to the result of that event. Okay, the ways that event can happen. So event A can be a 1, event A can be a 2, 3, 4, 5. So you roll a 1, and what do you do after you roll a 1? Flip the coin, so that can happen 2 ways. So we put 2 branches off there, heads or tails. So here's one outcome. Event A and then event B could be event A is a 1, event B is a heads. Event A is a 1, event B is a tails. So there's 2. We counted 2 so far, 2 of those outcomes. But we want to speed this up because for one, what if these numbers are bigger? So all these are heads, tails, heads, tails, heads, tails. This tree diagram is small enough that we can draw the whole thing and clearly see how many branch tips. There's 2 for every 6, so 6 times 2 gives us 12. 6 for the die, 2 for the coin, multiply them together, you get 12. So that's it. Fundamental counting principle is 6 ways this can happen, 2 ways this can happen, multiply them together. All right? We good so far? All right. Let's look at the next one. So just add more to it. You got a 6-sided die, a quarter, and a deck of cards. How many? Maybe not everybody's familiar with a deck of cards. How many cards are in a deck of cards? 52. 13 cards for every board, every one of the 4 suits. So there's 4 suits and 13 cards per suit. So that's 52 cards. So we're gonna. I know you may be already done. Maybe you already know the number, but I want to just visualize it, draw it out, at least part of it, so we can all see it with our eyes and not just be told about it. Okay. So event A is we're going to roll a die. So how many ways can event A have? 6. 1, 2, 3, 4, 5, 6. And actually, as the numbers 1 through 6 are the outcomes of that event. 2, 3, 4, 5, 6. Then we do what? And that can happen 2 different ways. 2 different ways. So every of the 6 branches gets 2 more branches, so now we're up to 12. And after you roll a die, flip a coin, you then do what? Pick a card. How many cards did you pick from? 52. 52. So I'm not even going to draw all these, but imagine that's 52 more branches. 52 more branches. How many times am I going to have to draw 52 branches? 12 times. Right? 6. But every 6 has 2 more, so 1, 2, 3, 4, 5, 6, 7, 8, 12. Every one of these is going to get 52. Oh, there's 2 times 6 times you have to do that. So 6 ways you can roll a die, times 2 ways that you can flip a coin, times 52 ways that you can pick a card, is how many ways that you can do all 3 in a row. 654. That's a lot. Sorry, 624. 624. Come on. There we go. I hope that's the last one.
What about Mr. 40?
So let's go over a little bit of vocab. If you can give me an example of, from this problem, like, what's an example of an event? Flip a coin is an event. Okay, so that's an event. What are the other two events? Draw a card, roll a die. Okay. Let's see if you picked up on what outcome was. There's lots of outcomes. Give me an example of an outcome.
6 tails, ace of spades.
6 tails, ace of spades. 6 flip tails, and you draw the ace of spades. There's an event. It's the 3 events happening in a row. So an outcome is a collection of events. This is going to become more useful when we talk about probability. Probability talks a lot about events and outcomes. So before we move on, just the last thing for this slide here, who can sum up what the fundamental counting principle is, tells us to do what? No, we're not playing the quiet game. We can stay the quiet the longest. I just want somebody to explain what the fundamental counting principle says. Tracker. Tell me about the fundamental counting principle. We've been using it. We've used it twice so far. What does it tell us?
It helps us figure out probability.
It certainly will do that. It hasn't done that yet.
Yeah.
Well, one thing it should do is count things, right?
Yeah.
What does it count?
Well, we count it because it counts it for us.
It does.
Outcomes of events.
Outcomes, all the numbers of outcomes?
Yeah.
Okay, counts all the outcomes, and it does that by taking the number of ways events can happen and multiplying those numbers of ways that the events can happen, right? You got 3 events, you're going to have 3 numbers to multiply together. Each number is going to be how many ways each thing, each event can happen. Okay, it's a bit of a wordy principle, but we can't really avoid it. So you take the number of ways that each event can happen, you multiply all those together. I had one more. So this one I'll give to you just to see if you know what's going on. Really simple problem. Just shout it out when you have the answer and be ready to explain how it is you got it.
Megabytes?
Huh?
Megabytes. It's so small.
Oh, you're right. You're right about that.
New iPhones these days?
Look, I grew up in the 90s primarily. Megabytes were like a big thing.
So like terabytes.
Did I tell you about my dad when he sold computers? He sold a computer in 90, well, we gotta be like 94, 95, that had 1.2 gigabytes of hard drive space. Like, even the smallest, 16 by the way, the smallest iPod available is, you know, close to 16 times bigger than a computer. I mean, we're talking about the thing that was the thing in your house. It was a computer. Oh my gosh, you have one. And it was 1.2 gigabytes. And then my dad was like, these people are ridiculous. You're spending ridiculous amounts of money on space they'll never use up. Now that's just like pictures. It's 1.2 gigabytes if you don't have very many pictures. Anyway, how many different, with gigabytes now, how many different iPods could you possibly put together?
36.
Got 36, and how'd you get 36? 3, so we'll call that the hard drive. It's not really a hard drive, but
Times 2 fronts
times 2 for the fronts,
and 6
6 backs, 36. All right, we feel comfortable? All good? Okay. And now we get into permutations. Permutations is just really an application of the fundamental counting principle, but you're just applying it to one group of things. If that made any sense, great. If it didn't, that's fine too. Okay. So permutations, we're putting stuff in a line. That's basically what we're doing. Putting some stuff in a line. Okay. Remember when I said order was important or order matters? Order matters means if we had the letters A, B, and C, and then we took A, B, and C and we rearranged them to C, B, and A, and A, C, B, but we count those as 3 different permutations. Okay? 3 different permutations. Okay. So you can think of it as like first, second, and third place. It's a really common one, or president, vice president, and secretary. Very common way to name these positions that things can fall into. So we'll talk about that first. So we'll start with the easiest type of permutation. And that would be where you take the whole group, as opposed to a subgroup, the whole group, and you just rearrange them in all the different ways you can rearrange them. Okay. So we'll start with 3 people. There are 3 people that are on a committee. This committee has 3 positions: president, vice president, and secretary. How many different ways are going to take these 3 people and rearrange them in all the ways that you can put them into these 3 positions? Notice how we're taking 3 people and putting them in 3 positions. Okay. Simplest permutation. How many?
6.
You got 6? How'd you get 6?
One person will be president.
Yeah.
And then vice president, secretary.
Yeah,
And
yeah.
then
Okay, so I'm going to president, vice president, secretary. Just write that way, kind of way you said it.
Yeah, and then the same person can be president, but then the vice president and secretary switched.
Oh, so you just kind of counted it.
Yeah.
You kind of went, so let's say we have, Adam and Barb and Carl. Okay? And, excuse me, if we put Adam first, then we could put Barb and Carl next. Or you could take Adam and put Carl, then Bob, or Barb, like that. And then you could do the same thing for Barb is first and Carl is first. Okay. But if there are 4 people, we get kind of hard to count, right? That way. Okay. So we're going to use the fundamental counting principle. Remember, the fundamental counting principle relies on multiplying the number of ways events can happen. So what we have to do is translate these questions into a series of events. Event 1, event 2, event 3, 4, 5, 6, however many events there are. Okay. First event is pick a president. Okay. How many ways can you pick a president? If nobody's filled any position yet, we're just going to pick the first person to be president. How many people? 3. 3 people to choose from. All right. So now you pick somebody for the president. How many people do you have to choose from for the vice president? 2. You can't have somebody be president and vice president. So somebody's been eliminated. And next, 1. There's the last person left. There's not really any choosing that happens here. We just, the last position is whoever's left over. So event P can happen 3 ways. Event VP can happen 2 ways. Event S can happen 1 way. So 3 times 2 times 1 is 6 different ways to arrange these 3 people. In a tree diagram, that would look like this. Okay, first you pick the vice president, you pick one of those 3 people. Okay, you can choose A, or B, or C. Right? After you pick A, you can pick B or C. Right? And after B, you can choose C, and after C, you can choose B. Yeah? Well, that's pretty much exactly how Jade was saying she's doing a tree diagram, just with letters. Right? After you pick B, you can pick A, or you can pick C, and after you pick A, you can pick C, or after you pick C, you can pick A. You get the idea. It becomes a tree diagram, and just multiply the number of branches times each other, and then we arrive at 6. All right. Let's see. Let's come up with another example. Let's just take the classic example. The people in this room. That's what a lot of teachers use. People in this room. So how many people do we have in the room?
16.
No, right now in this room. You look around. We got
No, with like a phone.
8 including me. Okay, 8 including me. So, we're gonna line up
Let's go.
to, who cares? We're gonna line up in order, okay? Somebody's first, second, third, fourth, fifth, sixth, seventh, and eighth, right? So 8 people. Okay, and we wanna line them up. All 8, that's important here, okay? All 8, not 7 of them, not 2 of them, not 4 of them, but all 8 of them. How many ways are there to order all 8 of those people?
40,320.
Okay, how'd you do it?
8 times 7 times 16.
You're seeing a pattern here.
4 times 3 times 2.
Exactly right. Event A is pick somebody to be first. Event B is pick somebody to be second. Event C is pick somebody to be third, and so on, all the way down the line. Until you get to the 8th person, and then just whoever's left over. The kind of cool thing about this to me is, one of these arrangements is from oldest to youngest. One of them is from youngest to oldest. One of them is from tallest to shortest. One of them is from loudest to most quiet. Taking the most loudest. One of them is fastest to slowest. Like every possible way that we can order people by some order, with respect to some kind of an order, is represented here. Right? And a lot of them just seemingly random. Right? So that's kind of neat. Now what about if we change it to, well, I'll just cross it out. Instead of 8 people, I just wanted to cross it out. Instead of 8 people, and lining them all 8 up, let's say there's 16 people, and we'll line up all 16 of them. How long is it going to take you to do this calculation?
Longer than
Longer than the last one, probably twice as long as this one, right? And have 16 numbers to multiply together. What numbers are we going to multiply together? 16, 15, 14, all the way down to what? To 1, 3, 2, 1. That's 14. And what if we change that to 100 people? Okay, All right. Anybody do this already?
Yeah.
Well, how big is it?
2.0922789988
Okay, let's interpret that correctly. 2.7?
2.09.
Okay, we'll just go with that. E to the what? 13. So that means times 10 to the 13th power, which basically means move your decimal place over 13 places. Big, very big number. That's past thousands, millions, billions, trillions. It's into the tens of trillions. Yeah?
So with like E, is E incorporated into this chapter? Or are we
What do you mean?
like E to like times 10 to the 13th? Because in chemistry, that's like the first thing that we learned how to use.
O times 10 to the 23rd?
Yeah.
Scientific notation? No.
No?
We already actually did the chapter that incorporates that. That was exponential growth. In, I don't know what chapter that was. 6? 7? Okay, so I mean, just 16 people. Is that a big number? That's not a lot of people. I mean, we have that many people in some of my classes, and there are tens of trillions of ways to arrange those 16 people in a line. Like, we would all die. Like, some immortal person would have to rearrange our bones for us to actually do this because it would take so long. It would take a crazy long time. So then if we go to 100, well, that just gets ridiculous, right? Okay. Well, let's not change it to that. Let's change it to 20. No, let's change it to 30. Just so it just, if I asked you to do it, you would moan and groan and complain. Just don't do it yet, okay? Because I'm going to show you the easy way. 30. Okay, first tell me how many different ways, like how would you calculate how many different ways there are to arrange those 30 people? All the way down, okay? When you say that, what you are really saying, like a faster way to say that, just like here's a faster way to say 2 plus 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 2. What's a fast way to say that?
To the something power?
Plus. 2 plus plus plus. 2 times 9. Right? 2 times 9 is a fast way to say 2 plus 2 plus 2 plus 9 times. Okay? So when you say 30 times, 29 times, 28 times, all the way down to 1, the fast way to say that is 30 factorial. 30 times 29 times 28 times blah, 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 all the way down to 3, 2, 1. So if we could communicate that to, say, a calculator, it would know exactly what we wanted it to do, and it would do it for us. Right? So it's just a matter of typing the numbers 3 and then 0, and then finding the exclamation mark, the factorial. Well, that's in math. And you can press the left arrow once or the right arrow twice, or 3 times. Anyways, get over here, highlight PRD. Move down to factorial, hit enter. Now it's ready, it knows what you want. It knows what you want it to do, 30 times 29 times 28 times 27 and so on. And then that's very big. You move this over 32 places. It's crazy, crazy big. What would that be, so.
A lot of zeros.
What?
It'd be a lot of zeros.
That would be, so thousands, millions, billions, trillions, quadrillions, centillions, sectillions, septillions, nontillions, and dectillion? I don't even know if there's a word for that. Dectillion's my best guess. So it would be in the hundreds of dectillions of different ways that we could arrange. It's just, I mean, just to give it some perspective, so this is times 10 to the 32, right? So this number, roughly this number, is the number of particles in the universe. Okay, so it's not quite that big, but it's getting close. 10 to the 86 particles in the universe. I just read something, what was it? There are more atoms, or molecules, water molecules, in a glass of water than there are glasses of water in all of the oceans of all of the planet Earth. So imagine how many glasses you could scoop up out of the ocean. It would be a lifetime pursuit. It would pass down to your heir and your heir's heir, and it would just be their job forever to scoop out all the water cup by cup. There are more than that number of atoms in just one cup of water, okay, or of water molecules. Okay. So that's a lot, just in a cup. Imagine how many that is. It's more than the number of cups you could take out of the ocean. And there's, this number is the number of particles in the observable universe. At least that's what they calculate then. Okay, so very, very large. Now, just want to talk about this then. What that means is, what does n factorial mean? N stands for some number, 30 or 16 or 8.
Raises times 10 something.
No,
You multiply down.
you multiply all the way down to 1. 10, or n times the number before that, times the number before that, times the number before that, all the way down to 1. Well, that would be n times, what comes before n? N plus 1 would be 1 more than n.
Oh, n minus 1.
N minus 1 would be 1 less than n. And after, like before that,
N minus 2.
n minus 2, that's how we would express that, all the way down to 3, 2, 1. Every factorial goes all the way down to 3, 2, 1.
Wait, it's decillion.
Hmm?
It's decillion.
What about it?
That's what it was. It wasn't dectillion, it was decillion.
Decillion?
Yeah.
Did you look it up or
I
something?
had a book.
Oh.
It was a pretty cool book.
Decillion,
It
okay.
had many information.
Now we know.
Had many information. Yeah. It had the 5 longest words in the English language and the longest one. It's like 1,000 letters.
Okay. This is n factorial. And it can be used for more than this, but it can be used to count the total number of permutations of n things. If you have n things and you want to arrange them in all possible ways, you just take it factorial. itself times the number before that, times the number before that, all the way down to 3, 2, 1. But next, we move into permutations, not of all the things, but of some of the things. So first I said it was just permutations. All I said it was putting stuff in a line. Okay, what I'm saying, there's a little more to it. What's more to it? It's this. It's not just putting all of them, but putting some of those things in a line, which is a little bit tricky. Okay. So let's talk about this problem. There are 30 runners in a race, in a marathon or something. Who knows? How many ways are there for the first 3 people to come in, for first, second, and third place? Okay. There's a permutation problem because order is important, right? Would you say order is important in this scenario? Or to ask you if it's important, I'm counting 3 people, right? Is the order of these 3 people important, or is it not? It is, because first, second, third, if you switch first and second place, well, the guy who wasn't first is not going to be very happy because he came in first, not second. Right? Order is important. If you arrange them differently, it's different. Right? ABC is different from CBA, is different from ACB, or any other way you can arrange those things. So how many ways are there for those 3 people to come in? If you think about it for a second, if you want to fill those 3 positions, you can use the fundamental counting principle to figure that out in not too long a time. So think about it for a second. Tell me what you come up with.
27,000.
24,360.
That's close.
What'd you come up with?
27,000.
How'd you come up with that?
30 times 30 times 30.
Okay. Almost. So your number's too big. We got 27,000. Your number's too big because, well, if you think about what you're doing, you're saying,
I see.
the first person comes in, and that's 30 possibilities. And then you're saying 30 is next, but that can't be because
Yeah.
one person's already used up. So it's 29 and then 28. 24,360. 24,360. That's how many different ways the top 3 people can finish out of the 30 racers. Let's make it a little bit harder. The number's a little bit bigger. Okay. Remember, I changed it from 8, not too bad. 8 times 7 times 6 times 5, 4, 3, 2, 1. You can multiply that together. Then 16, a couple of you even bothered to do that. 30, when there were 30 people all in a row, we realized this is getting unmanageable. It's not reasonable to multiply 30 times all the numbers before it. It just would take too long. So we came up with factorial, and your calculator knows about factorial. Okay. So we'll do the same again. We'll make the numbers so big that it's just not really reasonable to calculate it by hand like that. And what we're working our way to is that first formula that you wrote down, the permutations formula. Okay, so we'll start here. Like the more positions you're trying to fill, the harder this gets. Right? So there are 12 people to choose from. There are 4 positions to be filled: president, vice president, treasurer, and secretary. How many ways can the 4 of these 12 people be selected to fill these 4 positions? You got it, Jake?
11,880.
11,880. What'd you do to get that?
12 times 11 times 10,000.
Good. 12 times 11 times 10. 11,080. 11,880. I knew that was right somehow. 11,880. Let's say we change it to not 12 people, but 50 people. And it wouldn't be too hard to do 4 positions, right? 50 times 49 times 48 times 47, we're done. It's a big number, but it doesn't take long to calculate it. It's just 4 numbers multiplying together. So what if we up the number of positions? There are 22 positions. So obviously we don't have names for them right now. There's 22 positions to be filled. They could be overseer, certain thing. Now hold on, wait. No, don't just go crazy. Shouldn't there be an easier way? I mean, think, we're over our math history. I need your attention. I just really want you to pay attention so that you can be on board here. We started with addition, right? I gave you this example earlier. I started with addition. 2 plus 2. Easy, that's 4, right? 2 plus 2 plus 2. I can add those together, I get 6. Once I add 2 9 times, then we step it up to multiplication. 2 times 9 is the same as 2 plus 2 plus 2 plus 2, 9 times. Okay? Then we have, say, 2 times 2. Right? 2 times 2 times 2. 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2. We like you're doing multiplication multiple times, right? Then we say, well, there's got to be an easier way, right? What's the shorthand for multiplying things together lots, or itself? Or what's that? Divide would be subtracting. Exponents. 2 times 2 times 2 times 2 times 2. It's 2 to some power. Right? We keep every time something gets to be really big, we then come up with a notation to bring it back down and shorten it. Right? Like try to imagine doing exponents by addition. 2 to the 32 with addition. That's a lot. Okay? So that's what we're doing now. We're finding, well, if I was going to do 50 people with 22 positions to fill, well, that is, well, 22 like spaces, and I would have to multiply 50 times 49 times 48 times all the way down the line, right? Okay. And that, we would like to shorten that up, just like we have every other time we've ever done any kind of operation. So, first let's start with what we actually want to calculate, and we'll find a short way with factorials to calculate it, and we'll have made our formula. Okay, 50 times 49 times 48 times 47, and so on. Now we're going to stop somewhere, right? We're going to stop somewhere other than 3, 2, 1. We're not going to go all the way down to 3, 2, 1. So we don't want 50 factorial, right? That's my point. Correct? Where are we going to stop? What's going to be the last number that we multiply by? 28. So, you got the right idea, and like 100% of classes get that answer wrong the first time, because you need to realize this. So you did it by 50 minus 22, right? You got 28, of course. All right. But, like, all of these slots here, there's 22 of them. Yeah? Which means that 28, that's the rest. Right? Well, it ends at 1. Everybody following me? At the very end we have 1, and then it's 2, and then it's 3, and then it's 4, and so on. And it goes all the way up to what? 28. To 28, which means the last number that we want to multiply by for the thing we're calculating is actually what? 29. Right? Makes sense. 29 is where we want to stop. You good there? You got the first 28 right there, and the rest of the 22 actually starts from 29 up to 50 is 22 things. Okay. This also happens, like say I tell you to read, we're in an English class, and I say read pages 35 to 122. How many pages are you going to read? 35 to 122. Actually, not easy. 88. Right? 88. Oh, no. You're gonna. So this is thing where I say, actually, like, take this number through this number. How many numbers is that? It's actually one more than when you subtract the two numbers. Okay? Because you're actually counting that first thing, so it's one extra thing. You're not counting from this one up to that, you're actually counting this number and all these other numbers after. Okay. When we do 50 minus 22, we get 28 things, which means that actually if we're to multiply them together, we stop at 29. So you do 50 minus 22 plus 1. All right, so far do we see, I mean that's pretty trivial, that's not really the important thing here. The important thing we do, the important thing I want you to do is just to see what we want. We want to cut it off right there. Is that understandable? Okay. So we're going to multiply 50 all the way down to 29, which means we want to get rid of 28 all the way down to 1. Well, what is 28 all the way down to 1? When we multiply all those together, what's another word for that? Or another way to say it?
8 exclamation.
Right? But that exclamation point is read factorial, 28 factorial. So what if this is all multiplication, right? So if I want to cancel out multiplication, I use division. It's the inverse of multiplication. So if this altogether is 28 factorial, if I divide this by 28 factorial, that cancels out all of these factors. So to shorten it up, it's 50 factorial over 28 factorial. And how do we get 28?
We subtracted 22 from 50.
Right. We just took 50 minus 22, and whatever that number was, we threw a factorial on it, and it canceled all that bottom stuff. We want that top stuff. We want the top 22 positions to be all ordered. And we don't want those bottom 28. We want to eliminate those. We don't care about after you pick the first 29 or the first 22 positions. You don't care about the rest of it, so you don't want to count all of those. So what we did here is we used the permutations formula. This would be 50 p 22. That's 50 factorial over 50 minus 22 factorial. Or to combinations. So we're not going to do combinations quite yet. Here's another way we can think about it. Let's say that there are 32 flavors of ice cream. And we're going to take from those 32 flavors, say 6 of them, to put in like this giant platter. Okay. Actually, let's put them on an ice cream cone, because that kind of implies an order. It's important that order be important. So we're going to put them on an ice cream cone. Let's see. Quite good. Close it. I want to fill it in. That's not good. Black ice cream. That's some good ice cream. Probably gross. Ooh. That's mint ice cream. So from the 32 flavors, we're going to choose, or we're going to pick 6 to go on an ice cream cone. Now, it really depends on your opinion, but I'm going to say that order is important here. Okay, if my top flavor is chocolate, the first thing I'm going to eat is chocolate. Maybe I don't want to eat chocolate first. I'm going to save it for dessert. I'm going to save it till the end. Which is dessert of a bunch of ice cream. So anyway, you know, maybe that's chocolate and oh no, that's right. That's what I wanted. And then I got 3, 4, 5, and so that's got too big. And I have 6. We got some kind of a blue ice cream for some reason, and maybe a sherbet, and I don't know what purple is going to taste like, but we got some, and there's that black ice cream again. Let's get that out of the way first, whatever that flavor of black ice cream is. Then we'll eat our way down to the mint. Okay.
Yeah, bubblegum's pretty good.
Okay, that's bubblegum.
It's not that bad.
Oh, sorry.
It's got bubblegum
Yeah,
inside. Pink is bubblegum.
Okay, well, maybe this is bubblegum.
Got cookies and cream.
Well, that's 6 of the 32 flavors that they have, right? So we're not even looking at all the possible flavors that we could put on there. We're just picking 6 of them, and I'm going to go ahead and imply an order in that, saying, you know, if I eat some kind of ice cream first, you know, that makes a difference to me. Or I'm going to save my favorite ice cream for last. So it's important what the order of the ice cream is. So if the order is important, we're going to use permutations. Permutations, order is important. Permutation, the word permutation means ordering. Okay. So similar to this problem right here. This was 50p22. What would this be?
32p6.
32p6. And we don't really want to multiply these numbers by hand, so we would use the formula. The formula would look like what?
32 factorials over 32 minus 6 factorials.
Got it. 32 minus 6 factorial. Which would be 32 factorial. 26 factorial. So this 26 factorial is all the factors of all factors 26 through 25, 24, all the way down to 1. That's going to cancel all of the 26 through, did I say 21? All the 26 through 1 of the 32 factorial, leaving just 32 times 31 times 30 times, you know, just 6 positions. So how many ways are there if you walk into a 32 flavors, which doesn't exist?
652 billions, 458, I mean, sorry, millions.
Million. 652 million?
458,240.
A lot.
That's cute. That's cute. It's adorable.
Okay, so thus concludes permutations. Can we put a lid on that? Is that so that you can understand that if I ask you to find so many, how many ways can you order this many things out of this many things? Okay. Remember, that's when order is important. Scoops stacked up on an ice cream cone, that's some order. Vice president, president, secretary, treasurer, committee number 1, committee number 2, committee member number 3, first, second place, first, second, third place, whatever implies an order, that's where we would use permutations. But I also want you to grasp the idea that 32 factorial would be how we order all 32 of these flavors, a lot of ways. And dividing by 26 factorial eliminates 26 all the way down to 1. All of those last 26 we get rid of, leaving only the top 6 positions starting at 32, going down to 31, 30, 29, 28, 27. So now we're going to talk about combinations where order is not important. It doesn't matter what order they're in. It's all the same. So you tell me, if we say that order isn't important, if we go on and say like the order of these ice cream scoops is not important, it doesn't matter, would you think intuitively that that means that there's going to be more possibilities or fewer possibilities? If I said it doesn't matter what order these are in, would that to you mean there's more possibilities here or fewer possibilities? Fewer. Okay. So here's permutations. If I switch, this is going to look weird because they're weirdly on top of each other. But if I switch these two, I still have the same 6 things, the same 6 flavors, but that's different. It's a different order. Okay? But as far as combinations go, I didn't do anything. They are the same combination of 6 things. And no matter what order I put them in, it doesn't matter what order they're in. They're all the same 6 things. Okay? Putting them all in a different order, permutations, yes, those were all different permutations. Different combinations, no, it's all one combination. So how many combinations are there of these 6 flavors? How many combinations of these 6 flavors? How many, I mean, not talking about 32 flavors. If you just have 6 scoops on a cone, how many combinations are there of 6, of the 6? Just one. They exist. That's a combination. They exist in the same place at the same time. That's a combination. Put them in a different order, it doesn't matter. Okay, that's what it means by it doesn't matter. I'm beating a dead horse here and driving into the ground because it can be very confusing if it's not addressed. It was very confusing for me. I watched it be confusing for me and for fellow classmates and for students throughout the years. So I want to make sure we make that clear. Order doesn't matter means if I rearrange it, I haven't made anything new. It's still the same thing. All right. So let's talk about combinations. We're not putting some stuff in a line anymore. Let's say we're putting them in a group. A group doesn't really speak order to me. It doesn't say like, oh, it's important which order these things are in. Right? Hopefully that speaks the same to you. And here, just a reminder, order is not important in combinations, meaning that A, B, and C are the same as A, C, B, A, A, C, B. If you take those things and you rearrange them, you've done nothing new. It's not a new combination. So, for the past 2 years, or 2 years previous, I was in a disc golf club called the Garden City Flyers. And we would go out every Thursday, and a lot of times we would randomly pick from the big group that shows up. We would assemble flights. And like I say here, flights is a group of people that just go through the course together and play around together. All right? So that's what the word flight means. So, let's change the numbers a little bit. We changed it in the last class, and I think it made it a little bit better. So let's say a more realistic number, like 40 people show up, okay? And let's say that you don't want to get much bigger than this. You don't want to get much bigger than 4 people in a flight, so we'll just go 4. Okay. So you just, picture what's going on here. 40 people show up, and you're going to start picking from those 40. You're going to make a group of 4, okay? Could be these 4 guys, 2 from this group, and 2 from the second group. Put them together, they're a new group. Okay, but the order is not important. All right? That make sense? There's no first, second, third, fourth here. So let's start counting it. First, we're going to count it the old way, the permutations way. The order is important way. Okay, so how would we count it that way? With the, what would the formula look like? Okay, divided by there. 40 factorial. Now let's stop and pause and spell the flower. What does 40 factorial count?
40 times everything below it.
Yes. And like in the context of a problem like this, we're talking about people. Could you put it into describe the scenario? Like what does this count?
All the different combinations.
Well, it seems like combination would be a good word, but in math, permutations would be the right word. Permutations of what?
Number of groups that are possible.
Just all the people, like in a row. Like we're going to take all the people and just line them up in order, some order, I don't know, oldest to youngest, that would be one permutation. Tallest to shortest, probably another permutation. Shortest to tallest, yet another permutation. We counted 3 so far. And every other way that you could line people up in a row out of 40 people. That's what 40 factorial counts. Okay? But now we don't want all 40 people to line up. How many people do we want to line up? And eventually we will have them not being lined up. But first let's count how many ways there are to line up 4 out of the 40 people. So what did we do then? To get rid of all the ones that we don't care about, just keep the 4 that we do care about.
40 minus
Mm-hmm.
4 factorials.
That's right. That would be 36, right? So what that would do would be to get rid of, this is 40 times 39, times 38, times 37, times 36, and all the way down to 3, 2, 1. So 40 minus 4, which is 36 factorial, would get rid of all of those. So let's again pause and say, what have we now counted by taking, you know, after eliminating all this stuff, what we have is 40 times 39 times 38 times 37. What does that count? All the permutations, which means all of the ways you can put in a unique order. Okay, permutations of what? People. How many people? 4 people out of 40 people. So the number of ways you can take 4 people out of 40 and put them in all the different ways that you can put 4 people. Okay? Okay. So now let's look at what we have and what we wanted to get rid of. Okay? The number of combinations, like where order doesn't matter, is that going to be more or less than what we have right now, where order does matter? Yeah, what we want is less, actually a lot less. Okay. We don't want to count all the ways that you can order all these groups. Okay, so let me try and help you see like how much too much we have. Let's look at one group. Okay, there's lots of groups, but let's look at one group and what this is counting. Because it's taking each group and then it's counting it lots of different times. Right? So let's say we have all these people. We have person A, person B, person C, and person D. Now this is just 4 people. 4 of the 40. There are 40 people. So there's A through Z, and then 14 more people. New letters. Okay. So person A, B, C, and D. Just those 4 people. Now, if we count the way that you can order all 4 of those people, how many ways can you order just those 4 people? You'd have to use something we learned today to figure that out. Got 4 people there, people A, B, C, and D. And you just want to order them in all the ways that you can order those 4 people. It would be 4 factorial, yeah. So 4 factorial, that's how many ways? 24. All right. Now how many combinations is that? Get down to vocab here. How many combinations, out of the 40 people, how many combinations do we have so far? 1. Just a group of 4 people. Okay, now let's say we take people A, B, C, and E. Okay, so we get rid of D, and then we bring in E. Now how many ways are there to order those 4 people? Also 24. There are 4 different, well, it's a group it's a different group. It's a different combination. It's a unique group from this one. It's different from this one. It has 3 of the same people, but it has 1 different person, so it's different. That's what makes it different. We brought in a different person. But we are over counting it, right? We're counting it 24 times too much. How about the group A, B, C, and F? We're counting it 24 times. You get the idea? What's that?
Divide by 24.
So we'll divide by 24. And how did we figure out was 24? How did we get the number 24? 4 factorial, right? 4 factorial. So we divided by 24, 4 factorial. So in this case, what we've done is 40C 4. That's 40 factorial over, we have the normal 40 minus 4 factorial, and then we divide it by 4 factorial, or multiply this by 4 factorial and divide that by that. And you'll notice, like, if I do 40 minus 4, I get 36 factorial and 4 factorial, and 36 plus 4 is 40. Of course, it will always be the case. And let's take this to where we have a little more room to work for a second. There we go. So this is 40 times 39 times 38 times 37 times 36 all the way down to 3 times 2 times 1 over 4 factorial times 36 factorial. What I'm going to show you here is we can almost do this by hand. Because so much of it gets eliminated, right? Like, what is all this?
36 factorial.
That's 36 factorial. We have a 36 factorial that's dividing it. So 36 factorial cancels 36 factorial. And 4 factorial is 4 times 3 times 2 times 1. I'm just going to show you that everything in the denominator is going to get canceled out. There's going to be a factor to cancel out within the numerator everywhere. So 4 and 40, okay? 3 and 39, 3 times 13, okay? 2 and 10, and then there's a 1 down there. So in the numerator we cancel, or the denominator we cancel everything out, and if we just do 5 times 13 times 38 times 37, that's the number of ways that you can put together a flight of 4 out of 40. So how many is that?
91,390.
91,000? Okay, you said 300 and what?
390.
And 90. Let's check. Because you might have done it right, but you there's a good chance you may have done it incorrectly. Because, well, we'll look at it. So 40 factorial, we know where to get that. That's over down here. Divided
I
by.
have 2 different answers.
You did it 2 different ways?
Yeah.
Okay. So if I do it, this is the most common mistake. If you make a mistake, this is public enemy number 1 right here. Okay. Most common mistake right here. Your calculator is not going to do this. It's not going to take 40 factorial divided by the product of these two. What is the calculator going to do in this case?
Divide by 36 factorial first.
It's just going to take 40 factorial divided by 36 factorial, get that answer, whatever that is. Then it's going to multiply it by 24 factorial, which is not what we wanted to do. Right? So how do we fix this mistake? Parentheses over the denominator. Insert parentheses at the end. There we go. 91,300, that's what you said though, right?
Yeah.
390? Yeah, you got that. Hold on. Even better than that, if I want to do 40C4, then the calculator can do that too. 40, if we go to math, over probability again, look at what is right there above factorial, NCR. So 40 NCR 4, and it'll do the whole calculation for you. 91,390. So just before we put the lid on just the idea of combinations and the formula for combinations for NCR, could someone come up with a scenario where we would use combinations to count all the possibilities? I made one up. We talked about people being formed into groups to play disc golf together. Invent another one.
Freeze tag teams.
What's that?
Freeze tag teams.
Freeze tag teams. Okay, you don't need a leader or anything like that, right? No order is important. Is that right?
Mhm.
You don't need to put once you put people in a group, they're in a group. They don't need to be counted in order. Okay? So give some numbers here.
5 a group.
5 per group. And then what?
What?
Well, how many people showed up to play?
20.
20 people showed up?
Yes.
Now here's an interesting question. Let's talk about that, because it kind of takes us to our next idea. Now we have to, it kind of comes full circle, we're going to say, how many ways can this happen? And that's kind of the beginning when we talked about the fundamental counting principle. But then the ways that event A, B, C, and D can happen are so hard to count that we need to use combinations of permutations to count them in the first place, right? It's not so easy as, oh, there's 3 hard drive sizes, there's this many colors, and this many colors for the backs of iPods. The numbers actually are harder to count than that. So let's use that.
It was
So-
like freestyle.
What?
We played freestyle this morning.
We did? Okay. So 20 people showed up, 20 free staggers. Okay. 5, let's use numbers. 5 per team, which means obviously we're going to have 4 teams, right? So the question is not how many of one team can be, but how many ways can all these people be split into teams? Like how many ways can we make 4 teams out of these 20 people? So first we use the fundamental counting principle. There are 4 events to count and then multiply together. What's the first event?
First team.
What's that?
The
First
first team.
team. Team 1. Then you pick team 2. Then you pick team 3. Then you pick team 4. Right? Let's imagine we got all done. We're down to team 4. How many teams can you make for team 4? Just 1. The 4 people who are left didn't get picked, right? Those sad people. So just 1 team can be made of the people who are left. Get the idea? Some people are getting eliminated, and there's only so many people left. Let's go all the way to the beginning here. How many team number 1s can you pick? Just 4? Yeah, different combinations of these people. So give it to me in NCR form.
Yeah, 20 NCR 5 is 15,504.
20C5.
Oh, just 20 C5.
What did you say?
I said, I put NCR.
Yeah.
Oh.
Your calculator is not, there's just a difference between how you write it and how you type it into your calculator. Yeah.
It was 15,504.
Okay. 15,504. Okay. Team number 2, that's a little bit different. How many ways are there to pick team number 2? Given the idea that some people are already picked.
What do you have to do, like 20 NCR 4?
Well, 20C4 would be making a team of 4 people with 20 people to choose from. 15C5, right? Now we have a pool of 15 people, but still we're picking 5 out of the 15. 15C5. Now, 10C5. And that, what would that be in terms of NCR? 5C5. So 5C5 or 10C10 or 20C20 or 11C11 is always 1. How many combinations are there from all of the, well, the one whole group is the only combination that exists. So this is 15,504. How much is this?
3,003.
And how many is this?
252.
And of course this is 1. So how many total?
What is that one together?
Multiply them.
1.1732 times 10 to the 10th.
So really a lot, right? Into the 10th, so we're past billion, like the tens of billions of ways that we could put together 4 unique teams. That's a lot. So there are going to be things like that. Let's do. We've got some time. So let's talk about like a really common combinations problem. So we talked about cards, 52 cards, 4 suits, 13 cards per the 4 suits, and that makes it your 52. So let's count every possible 5-card hand. So I'm the dealer, I deal you out 5 cards, we take up those 5 cards, we start playing. How many, out of those 52 cards, how many 5-card hands can you possibly make? And before you give me the number, just give me the, like, first of all, is it permutations or is it combinations? Does the order matter when you are dealt cards? No. Okay. It might seem like order is important because some hands they need to be in an order, like 2, 3, 4, 5, 6. That's an order, right? But it didn't matter how they got dealt to you. So it's a permutations or combinations problem. Combinations, not important what order they come in. So that would be what? C what? 52 C5, and that's how many?
2,598,960.
It's a lot of hands, right? And some of them are very good, like a straight, flush, and a lot of them are completely useless, except for maybe like if you have the highest card, then you're lucky enough to win. So there's a bunch of junk hands out there, and then there are some good ones. Do you know what a royal flush is? Anybody? Royal flush? What's a flush?
10, Jack, Queen, King, Ace, all the same suit.
That's a royal flush. A flush is just all the same suit, all 5 cards in the same suit. Royal flush would be 10 through ace in the same suit, right? Yeah. Okay. So, how many ways is that possible? How many royal flushes could there possibly be? Specifically 10 through ace. Yeah. So there's 1 per suit. So 4. So what is the probability that you'll get a royal flush?
You'd have to get 5 cards out of 52 cards, right? 5
Well,
specified cards.
how many royal flushes are there possible?
4.
4. And how many hands are there possible?
So you multiply that number by 4.
No. Because that's all the possible hands. There's not any more hands than that, right? The royal flushes are a part of that.
Times
There's
4
4
times 5.
out of those 2,598,960 total hands. Right? Familiar with probability? If there's a die and there's 6 different ways you can roll it, there's a 1 out of 6 chance you'll get a 2. A 1 out of 6 chance you'll get a 5. And a 3 out of 6 chance you'll get an odd number. Right? There's 3 odd numbers, 3 even numbers, 6 numbers total. 3 out of 6 that will be odd. There's only 4 royal flushes possible, and spades, kings, spades, hearts, diamonds, clubs. And here's all the possible hands you could ever make. So that's why it's really good to get a royal flush. There's only 4 ways out of almost 3 million. Alright. One more kind of problem, and then I'll just let you be. It'll be a card problem again. You're gonna put together a 5-card hand, a specific kind of designation. I'm just gonna take it right out of here. So we're gonna get 1 ace and 4 cards that are not aces. All right, so first we want to be dealt an ace. Right? So how many ways can we be dealt an ace?
4 out of 52.
Okay, just 4, right? There's 4 aces. There's 4 ways you can, so you're talking about probability. So 4 ways to get an ace. All right, and then what do we do? What do we get next? cards that are not aces. Does it matter what order they come in? This is a permutation or a combination problem. Combination. So we're going to count this using combination. So we get our one ace here, and we get 4 not. That's a mathematical symbol for not aces. So how many ways are there for that to happen? You get 4 cards that aren't aces. Order's not important here. 48 ways? No, because there's 48 ways to get one card that's not an ace. So there's 48 cards that are not aces, right? So these are the cards we want to take from, right? Just like here we wanted to take from 52 cards. Here we wanted to take from 20 people, or 15 people, or 10 people. Or we wanted to take from 40 people. Here, we're going to take from 48 cards. How many cards do we want to take? 4. 4 cards that are not aces, right? And is it a combination or permutation? It's a combination. So we're going to take from 48, in a way that order doesn't matter, 4 cards. 48 C4. So there's 4 ways that you can get an ace. There are 48 C4 ways that you can get 4 not aces, and you multiply it all together. How many ways is that? That's right. Four times. I'll just put parentheses around it to be safe. 48. Go to math, probability. These combinations. 4. I said that was the last one, but I also should mention something other, or it can be confusing. Factorials, when we're dealing with factorials multiplied by each other, added to each other, subtracted from each other, divided by each other, they don't go together in very nice ways. Actually, they don't really go together at all. Okay? What I mean by that is if you have 2x plus 3x, you get 5x. Okay? That makes sense. You got 2 x's and 3 x's, all together you have 5x. You got 2 apples, 3 apples, together you have 5 apples, whatever. But if I have 2 factorial plus 3 factorial, that is not 5 factorial. We're not saying we have 2 exclamation marks and 3 exclamation marks, and together we have 5 exclamation marks. This is 2 times 1, and we're adding, that's one thing, we're adding, we're not multiplying. Factorial is a multiplication kind of a deal. It's in that realm, not addition. And this is 3 times 2 times 1. And 5 factorial, which is not the same, it's 5 times 4 times 3 times 2 times 1. They're completely different things. We need to find 2 factorial and 3 factorial and add them together, and there's no way to shorten that up and just make it easy to find. Okay? Similarly, 5 factorial times 4 factorial. At the end of the day, you just need to do 5 factorial times 4 factorial. That's all that there is to do. Okay? It is not 20 factorial. I mean, just try it for yourself. Take 5 factorial, take 4 factorial, calculate those separately, multiply them together. You will get a relatively small number compared to 20 factorial. I mean, think about 20 factorial. It has 5 factorial in it. Okay? But it's also multiplying it by 6 all the way through 20. That's a very big number. This has 5 factorial in it. Okay? It's not, this isn't getting multiplied by 6 through 20. It's just getting multiplied by 4 through 1. Very small. Very different from being 20 factorial. Okay? These are not the same thing. Basically, they just don't go together very well. If you want to cancel things out, you have to write it out the long way. Things like 20 factorial over 13 factorial. That is not whatever, like, you don't just take 20 divided by 13 and throw a factorial on it. First of all, that won't mean anything because it'll be a decimal. There's no such thing as like 1.2 factorial. It's only 1 factorial, 2, 3, 4, 5, 6, 7, 8, 9, 10 factorial. So to figure this out, to combine these together, you would just have to write 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 all the way down to 3, 2, 1. And then realize 13 factorial cancels out 13 factorial. And this is actually what's left over. And it's not any kind of factorial. Right? You cannot just put a number in there factorial and be done with it. If anything, this, the fastest way you can calculate that would be 20, 20C7, or sorry, 20P7. That's how you could get the calculator to multiply those numbers together for you quickly. Also 3 times 7 factorial is not 21 factorial. 21 factorial is huge. If you've been doing these at all and messing around with your calculator, you know 21 factorial is going to be a very big number. 7 factorial is relatively small compared to 21 factorial. And if you take 7 factorial, just multiply by 3. It's not going to do anywhere near 21 times 20 times 19 times 18 times 17, all the way down to 1. So again, moral of the story, factorials don't go together. They do not combine nicely. You can't add them together. You can't multiply them together. You can't cancel them super easily. 2 factorials don't go together to make a factorial. Okay. So that's what I wanted to mention, so that you don't go home and say, well, why is it 3 times 7 factorial, 21 factorial? Just, if there's a factorial, calculate it separately, calculate the other one separately, and then do whatever with it. That's it. Any questions? All right. So yeah, you got a few minutes to do your homework.